So example of computing C from different y's. Run program. Okay, a number of times. I think it's 4 times get y1 equals 0, 1, 1, 0, y2 equals 1, 1, 0, 1, y3 equals 1, 0, 1, 1, and y4 equals 1, 1, 1, 1. So I think the best way to explain this is not, do an example and explain the general principles following the example rather than trying to explain the general principles. How many possible C's after each y? Well, 0, 1, 1, 0. We're eliminating all C's which are perpendicular, all values of C which are not perpendicular to this. So, if we take C and multiply it, if we take a random C, which is actually, C had better not be 0, so there are 15 possible C's. If we take a random C and multiply it by y1 equals 0, 1, 1, 0, well, there are 2 possible answers, either 0 or 1. Start, well, there's 15 of them, because C could be anything that's not all zeros. After the first one, we get 0, 1, 1, 0, and it turns out that out of all possible 16 values, there are 8 which are perpendicular to 0, 1, 1, 0. And of course, we can eliminate the all zeros vector, so there are 7. After the next one, 1, 1, 0, 1, the things that are perpendicular to both of this, and to both this and this, form a 2-dimensional subspace. And a 2-dimensional subspace has size 4 because 2 squared is 4. And so the number of possible things is 3. After 1, 0, 1, 1, well, you might think it goes down further, but actually it's 3. And that's because 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1 are not linearly independent. Good? Because if you take this and you add it to this, you get this. So let's call these y1, y2, y3. And we have y3 equals y2 plus y1, which means c dot y3 equals c dot y2 plus c dot y1. So if both of these are 0, this is also 0. So because we were unlucky and got a dependence here, the number of possible C's doesn't go down any further. But at y4, 1, 1, 1, 1, 1, 1, 1, 1 is in fact independent of all of these. So y4, y2, and y1 form a 3-dimensional subspace. which means there's only one non-zero vector perpendicular to this three-dimensional subspace, and that is C. So probability of finding C after n minus 1 iterations is, well, this last one let's see. So what we need to do is we need to make sure all of these are linearly independent. So the first step, it always works, 1, because everything here is linearly independent. Here, there's only one vector in this subspace, or one, let's see. So yi can be 0, actually. If yi is 0, then this doesn't help us at all. So the first time, so the first time we get 15 out of 16 good ones. The second time, well, there are now 2 vectors that don't help us because there's an all zeros vector and y1. So that's 7 out of 8 times. Now there's the third time, there are 3 vectors that don't, 4 vectors, 1 vector, 2 vectors, 4 vectors that don't help us. So this is 3 out of 4 times 1 out of 2. So for okay, something is 15, 7, 3. No, this last, we don't need that last 1 out of 2. 15 sevenths, 7 eighths, 3 fourths, because here, this last vector, there were okay, it's something like this. Let's think about this carefully. The first time, the only vector that can go wrong is 0, which is 15 out of 14. Yeah. So it ends with 3 over 4. It would end with 1/2 if you were trying to narrow it down to get 4 independent vectors. And it doesn't do that. It ends at 3/4. Because when you have a subspace of size n over 2, there's 1 vector left that is perpendicular to the subspace. For arbitrary n, probability is 3/4 times 7 eighths times 15 sixteenths times ... times 2 to the n minus 1 over 2 to the n. And this converges. And I was going to prove this converged. So this is 1 over 1 minus 1/4, 1 minus 1/8, 1 minus 1/16, 1 minus 1 over 2 to the n is approximately equal to e to the minus 1/4, e to the minus 1/8, e to the minus 1/16, ... e to the minus 1 over 2 to the n. And that is equal to e to the 1/2 minus 1 over 2 to the n. And I guess that is bigger than e to the minus 1/2. So it actually has a reasonable probability of converging. And of course, all of these are approximations, but they don't actually affect the value of the probability that you've converged after n steps. And if you really want to make sure you've converged, you run it for n plus log n steps, and or you just run it until you get n minus 1 perpendicular values of y sub I. So I won't do any more probability of success, but it's possible to show that this algorithm succeeds, and the expected time it takes is not much more than n iterations. Okay, so here we are. So the next thing I wanted to do is explain why all of these y sub I, how you can actually take these y sub i's and get C. And the answer is Gaussian elimination. And it might work a little bit differently for this, but we'll do it. So how to find C? Well, we know C dot y1 is 0. What does that mean? Y1 tells us that C2 plus C3 equals 0. Because y1 we have c2, y1 dot c is just c2 plus c3. And y2 tells us that c1 plus c2 plus c4 equals 0. c2 plus c4 equals 0. Y3 tells us that c1 plus c3 plus c4 equals 0. And y4 tells us that the sum of all of them is 0. C2 plus c3 plus c4 equals 0. So what we're going to do is we're going to take these equations and eliminate variables one by one, which, if you remember Gaussian elimination, that's how it worked. So let's hope this works. Okay. I screwed up doing this in my notes, so I'm just going to be doing it on the board so I could easily make a mistake. So let's eliminate the first variable first. So get rid of C1. Rid of C1. Well, we know C1 equals C2 plus C4 from Y2. And now Y1 gives us C2 plus C3 equals 0. Y2, well, we're using this equation to eliminate C1, so we won't worry about it. Y3, we take this one and we subtract this one. We get C2 plus C3 equals 0. Which is a duplicate of this equation. And the reason it's a duplicate is, you remember, y1, y2, and y3 were not linearly independent. And y4, we subtract this equation from this equation, And we get C1 plus C2 plus C4 cancel out. We get C3 equals 0. C3 equals 0. OK, so now we repeat. Well, we only have two equations left. We have C2 plus C3 equals 0 and C3 equals 0. So we can eliminate C3 from, we can take y4 and subtract it from y1 and get C2 equals 0. So we get C2 equals 0, C3 equals 0. Plugging back in here, we get C1 equals C4. And we get we get C equals 1, 0, 0, 1. So what are we doing? Well, assuming all the yi's are independent, we're eliminating one variable at each step. So we start with, I guess, n minus 1 equations and n variables. And we're left with one variable and no equations, except we get all these equations for Ci equals, for C1 in terms of later variables, and then for C2 in terms of later variables, and C3 in terms of later variables, etc. So we get an equation that looks like C1 equals C4. And so we only have one variable left, and we can either set it to 0 or 1. If we set it to 0, we get y equals 0, or we get c equals 0, which we know is the wrong answer. So we set it to 1, and we get c1 equals c4. So we're eliminating one equation and one variable at each step of this Gaussian elimination. And as long as we started with n minus 1 independent variables, we end up with a unique C. So this is just like Gaussian elimination for solving linear equations, except you don't have any fractions because the only thing you're dividing by is 1, which is much nicer. So this is indeed works. OK. So yeah, so I wanted to make sure that 1, 0, 0, 1 was perpendicular to all these vectors. Indeed, 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 indeed. So we got the right answer.